we've talked about polar bonds where the electrons are not shared equally. In a diatomic molecule that has just two atoms, if the bond is polar, then the whole molecule is polar. So here's a hydrogen chloride molecule. Chlorine is more electronegative than hydrogen, and so chlorine hogs the electrons in this shared bond. So this end of the molecule is going to be a little bit more negative, and this end is going to be a little more positive. And so we can draw it this way in terms of electron density. There's more electron density on the chlorine end and less on the hydrogen end. We can indicate with a delta plus or a delta minus which end is positive and which is negative. Any questions? If we have a polyatomic molecule, more than two atoms, then the polarity of the molecule is going to depend on the geometry of the molecule. It's going to depend on the shape. Because you could have the dipole moments of the individual bonds cancel each other out. And then even though the bonds are polar, the molecule as a whole could be nonpolar. Let's look at carbon dioxide. So here's the structure for carbon dioxide. If we were doing a Lewis structure, we'd see that there's two lone pairs on each of these oxygens. That doesn't, it's not that important for looking at the polarity because we've already decided that this is a linear molecule. Because on the central atom, there are two electron groups. Two groups get away from each other by being on opposite sides. Let's get rid of those electrons. So this carbon-oxygen bond is polar. Oxygen's more electronegative than carbon. The oxygen end will be slightly negative. The carbon end will be slightly positive because oxygen is hogging the electrons. In this other carbon-oxygen double bond, the oxygen is also hogging the electrons. And so this bond is pulling the electrons to the right. But those two forces offset each other. So you can think of playing tug-of-war, right? And here's oxygen pulling this way, and this oxygen pulling that way, and carbon stuck in the middle, and he's just getting his shoulders dislocated, right? But he's not getting pulled in one direction or another. There's no net movement because the forces oppose each other. Okay, a more math description is that dipole moments are vectors. They're vector quantities. They have a direction and they have a magnitude. So here, the directions of these vectors are exactly opposite, 180 degrees. They're pointing in opposite directions. Their magnitudes are equal because the electronegativity difference between carbon and oxygen is the same as the electronegativity difference between carbon and oxygen. Right? And so they're going to cancel each other out. So overall, this molecule does not have one end that's more positive or negative than the other. You could say, well, the middle is a little more positive and the ends are a little more negative, but that's not really going to matter. It's the molecule overall doesn't have one end that's more negative. Any questions? Let's look at water. So here we have a model of water drawn according to the molecular shape of water. Water is a bent molecule, right, because of the lone pairs. So it's bent. Each of these bonds is polar. Oxygen's more electronegative than hydrogen. So oxygen is pulling the electrons from hydrogen, and oxygen's pulling electrons from the other hydrogen. So overall, oxygen is pulling the electrons that way. This oxygen end is partially negative. The hydrogen end is partially positive. The molecule is bent. Those dipole moments do not add up to zero. It has a net dipole moment given by this dashed line here, the dashed arrow. Any questions? So we need to be able to identify if a molecule is polar or not. This is important because whether a molecule is polar or nonpolar has a lot to do with physical and chemical properties. And so it's an important thing to be able to do. So first of all, you draw the Lewis structure, you determine the molecular geometry. You've got to know the shape of the molecule. Then you look and see if the molecule has polar bonds. A lot of molecules do have polar bonds. Indicate the polar bonds with vectors pointing toward the more electronegative atom, and have the length be proportional to the chain difference in electronegativity. Then figure out if the polar bonds add together to form a net dipole moment, or if they add to zero. If they add to zero, the molecule's nonpolar. If there is a net vector, then the molecule's polar. Well, most of you probably don't remember how to add vectors. So we're going to go over vector addition. In one dimension, the vectors are on a line. So you can have the vectors going in the same direction. You can have the vectors going in opposite directions. You could have both of them going to the left, both going to the right, or one going right, one going left. Those are the three possibilities. If they're both going in the same direction, that's going to add up, and you're going to have a net vector. Here in example 2, we have the vectors going in opposite directions, but this one is bigger than that one. I think for those of you that aren't great with math and vector addition and things, I think thinking about tug-of-war is helpful. So in this example, you have two people of equal strength pulling in the same direction. Their efforts are going to benefit each other, and the result is they're going to pull more strongly in that direction, right? Here you have two people pulling in opposite directions, but this guy is twice as strong as this person. So if you imagine, you know, the people with that rope and the red line in the middle of it, the red line on the tug-of-war rope is going to move in the direction of the stronger person, right? When we add these, it's like adding a negative number and a positive number. If we have a negative 5 and a positive 10, we end up with a positive 5. There's a net vector. In this example, we have the vectors going in opposite directions, and they're equal in magnitude. So here you have two people of equal strength pulling in opposite directions on the tug-of-war rope. Nothing happens because their efforts add up to 0. Any questions? What if you have 2 dimensions? In 2 dimensions, you draw a parallelogram in which the two vectors form two adjacent sides. So if we're adding this vector A and this vector B, we're going to take and draw a parallel line to A, same length, and a parallel line to B, the same length as B. And then the sum of the vectors is going from this corner to that new corner, the far corner. And that's adding vectors in 2 dimensions. What if you have more than 2 vectors? What if you have 3 vectors or 4 vectors? You add them together 2 at a time. So here, adding these 3 vectors, A, B, and C. You might first add A to B and get R. And now you're going to take R and add it to C, and that's going to give you R prime. And so the net vector is in this direction. It's a little harder to look at this and say, is there a net vector? The good thing is that we don't really care about how big the net vector is. We want to know the direction, and we want to know that there is a net vector or there is not. Just looking at these, I think we can tell that those are not going to cancel each other out, right? So there's a net vector here. Here we have 3 vectors. They're all of equal magnitude. The arrows are the same length, and they're pointing off at the corners of a triangle. If I add these two together, I get that vector, and then when I add that one to this one, they add up to 0. Any questions? Do you want to see it? Pardon me?
This is for like pulling on electrons?
It's pulling on the electron density. So the polar bonds where the electron density is not symmetrical, one end of the bond is more negative than the other. In some molecules, that adds up to make the entire molecule polar, and in other cases, the polarities cancel out, and you end up with a nonpolar molecule.
So H2O is polar there because they're pulling at that angle, and
Yep.
this makes that vector going down smaller than the vector going up. Right?
Well, so when I add, if I take two vectors, like, well, that, so these would be the vectors for water, right? It's hard to add them when their points aren't in the same place. So you can move the vectors to do vector addition. And then I'd make this dotted line here and a dotted line there. I'm not very good at dotted lines. And then the sum would be this. So here are some common cases. If you have a linear molecule and the dipole moments or the bonds are the same, you're going to have a net 0, and it'll be nonpolar. If you have trigonal planar and it's the same kind of bond, the same dipole moment for each, it's going to be nonpolar. If you have a tetrahedral shape and all the bonds are the same, then you're going to have a nonpolar molecule. If you have a bent structure with polar bonds, it's going to be polar because they can't cancel each other out. If you have a trigonal pyramid with polar bonds, it's also going to be a polar molecule. Yes?
Is that the seesaw?
No, this is not the seesaw. That red is adding the 3 blue vectors. Okay, I thought I had this slide in here, but I don't. Would you like an easier way? Yeah, okay. A molecule is nonpolar oh, I thought the lines would help me write straight. They're not. If both are true. Both. 1, no lone pairs on the central atom. And 2, all atoms bonded to central atom are the same or have the same electronegativity. Wow, that's a mess. A molecule is nonpolar if both of these things are true. There's no lone pairs on the central atom, and all the atoms that are bonded to the central atom are either the same element or their electronegativities are the same. No lone pairs gets us a symmetrical molecule where all the vectors go off in equally spaced out directions. All the atoms bonded to the central atom being the same means that all the vectors are the same length, and so they'll add up to 0.
So if you had CH4?
Yeah, let's do a quick example down here. So if I have CH4, this is methane, and that's the Lewis structure for methane. Are there any lone pairs on the central atom? No. Are all the atoms bonded to the central atom the same? Yes. There are no lone pairs. All the atoms are the same. This is nonpolar. So this is a nonpolar molecule. It's tetrahedral too, exactly. What if we had a chlorine on there? Chloromethane. Are there any lone pairs on the central atom? No. Are all the atoms the same? No. So no lone pairs, but the second condition is not true. This molecule is polar. Because, well, let's do the vectors. So the vector to chlorine is smaller than the vectors to with the hydrogens. And actually the carbon-hydrogen bonds are so close in, carbon and hydrogen are so close in electronegativity that they're essentially nonpolar bonds. And so these vectors then add up to something in one direction. Here, all the vectors are going to cancel each other out. They're going to add up to 0. Okay? So this will get you through most of the stuff, deciding if it's polar or not polar. So let's do this example. Determine if carbon tetrafluoride is polar. You've got to have the Lewis structure, because you have to have the molecular shape. Yep. So there's our Lewis structure. What's the molecular shape of this? It's tetrahedral. Are these bonds polar? Yeah, they are. So if we were going to draw them, we'd have one going up and one coming over here and one coming out at us this way and one going back that way. It's symmetrical.
I thought we said if they always stay on the right spot.
Yeah, I did say that.
What was that?
I'm trying to show it. If there's no lone pairs, then all the atoms are the same. So from my cheaty method, we'd say this is nonpolar, and it is. I'm trying to show you why. So this is a tetrahedral molecule. But each of these is the same length, right? Because they're all carbon-fluorine bonds. These bonds are polar. Fluorine is very electronegative. It's pulling the electrons. So you've got 4 guys pulling on this carbon, pulling the electrons. But they're pulling in directions that cancel out. Okay? Does that make sense?
How do you know if the bonds are polar? Just by the electronegativity of the element?
By the difference in electronegativity. And just, you know, as a rule of thumb, because if you have a table of electronegativities, then you can actually look at the differences. For the purposes of this, which is actually mostly why we need to think about electronegativities and polar bonds, I would say that if the 2 elements are not the same element, call it a polar bond. So this would definitely be a polar bond. In the previous example I did with methane and with chloromethane, the carbon-hydrogen bonds are not actually considered polar bonds. But if you use the rule of thumb and say, well, I'm going to call them polar because carbon and hydrogen are not the same element, you still end up with the correct answer for whether the molecule is polar or not. It'll work probably 95% of the time, which is pretty good.
And carbon is nonpolar because it doesn't form a polar bond today because its electronegativity is so low. It could lose organic electrons.
Well, no, carbon does form polar bonds.
I just meant like it has very low electronegativity.
It has a low electronegativity.
And hydrogen does as well.
Right. So polar and nonpolar molecules have very different properties. Oil is nonpolar, water is polar. Oil and water don't mix, do they? Italian salad dressing, right? It's got vinegar, which is acetic acid and water, and it's got oil, and then there's the spices and stuff. And you shake that bottle up, and it looks all shaken up, and you set it down, and you can watch it separate, right? Why does it do that? Because the oil is nonpolar, and the water is polar. Water has a negative end and a positive end. And the positive end of one water molecule is attracted to the negative end of another water molecule. And so water molecules tend to stick together a lot more than, say, oil molecules do. They're very attracted to each other.
Does that depend on the state, like gas?
Well, this attraction between the water molecules has a direct effect on the boiling point and the melting point of water. I want to get some of these marbles someday. So these solid colored marbles are magnetic marbles, and these are regular glass marbles. And if you just dump them all together, the magnetic marbles clump up and they exclude the glass marbles, right? Do you have to do anything? No, they just do that naturally because there's a strong attraction between the magnetic marbles that the magnetic marbles do not have for the glass marbles. And the glass marbles really have no attraction for each other. They're just, hanging around on the table, right? Water molecules, because they're polar, are like little magnets that are attracted to each other. So the water molecules are so attracted to each other that they exclude the oil. They push it out. And that's why the oil goes away. The reason the oil goes to the top is because it's less dense. But this is a little bit like high school. I don't know about you, but I'm really glad that I'm not in high school anymore. Man, you couldn't pay me enough to do that again. This is those clicky people, right? The cliques, right? Grown-ups still have cliques, but you just have more choices about avoiding them. So these people are very cliquey. They really like each other, and they're, if you're not part of the clique, they're just not going to talk to you. And so you just get pushed out, literally, right? So polarity is really important. Soap. Have you ever wondered how soap works? Bubbles. Bubbles are nice, but you can have soap without bubbles. So if you've ever greased a pan, like to make a cake or something, you have Crisco on your hands, you get butter on your hands, you know that you can't just go to the sink and rinse it off with water, right? If your hands are sticky because you were eating jelly beans or something, you can just rinse it off with water. It's no problem. But butter and Crisco are oils. Same goes with grease. You change the oil on your car and you get all engine grease and stuff on your hands. It does not want to come off. Water is polar, grease and oil are nonpolar. They don't like to mix together. So enter soap. This is an illustration of a soap molecule. A soap molecule has this long nonpolar tail. So this is carbons and hydrogens, very symmetrical, and also all of those bonds are nonpolar. And at one end, we have some oxygen atoms. And so this end of the molecule is polar, and this end is nonpolar. So this end gets along really well with water, and this end gets along really well with the soap. I'm sorry, it is the soap, with the grease. Okay. Another analogy I have for polar and nonpolar molecules is that they speak different languages. Okay. So my ancestors came from Sweden. My husband's ancestors came from Japan. So I'm going to pick on those two ethnicities and hopefully not get accused of anything. So if you had a bunch of Swedish people who only spoke Swedish and a bunch of Japanese people who only spoke Japanese in a room together, would they mingle thoroughly? No, you'd have clumps of Swedish people speaking Swedish and clumps of Japanese people speaking Japanese. What if you brought in a bunch of people that were fluent in both Japanese and Swedish and could translate for everybody? Well, that's going to help things out a lot, right? So what happens is the nonpolar tail gets into the grease, and the polar head sticks out. And so they make what are called micelles. And so you've got your little glob of grease here. Let's do a different color for the soap. And so the nonpolar tails of the soap will stick into the grease. You can see why I didn't go into art. The nonpolar tails stick into the grease. They dissolve in the grease just fine. And then the polar heads are on the outside. And the polar heads can communicate with the water and get along. And so the water just lets it through. Because, oh yeah, we communicate, we're talking. There's attraction. And so the soap breaks the grease up into tiny pieces and enables it to be washed away. Any questions? Chemistry in action in the bathroom.